Today, I will present a comprehensive case study under the topic of digital twin applications in planning. We will analyze the specific article, Urban Development with Dynamic Digital Twins in Helsinki City, published in IET Smart Cities. We will explore how Helsinki has transformed from using static 3D models to becoming a global leader in dynamic digital twin technology. Our roadmap is as follows. We will first define the difference between a simple 3D map and a dynamic digital twin. Then, we will look at Helsinki's journey and the technical challenges they faced. We will examine the Kalasatama district as our primary example, focusing on energy analysis and citizen engagement. Finally, we will wrap up with a summary and a class assignment. By the end of this session, you will be able to distinguish between a static model and a dynamic twin. You will understand the technical standards like CityGML that make these systems work, and evaluate how real-time data improves energy efficiency and helps citizens participate in city planning. Before we discuss Helsinki, we must clarify the concept. A traditional 3D model is just a picture. A semantic model adds information. It knows a building is a school made of brick. But a dynamic digital twin, which is our focus, adds real-time data. It knows the school is occupied right now and consuming X amount of energy. Let's officially introduce our case study, the city of Helsinki. Helsinki is not new to this technology. In fact, they are global pioneers who have been experimenting with 3D modeling since 1985. However, the real game changer came with the project we are analyzing today, Helsinki 3D Plus. Unlike many other cities that keep their data private, confidential, Helsinki took a bold step in 2016 and released their entire 3D city model as open data. This means anyone, from university researchers to software developers, can access and use this digital replica. The city's strategic goal goes far beyond just making a pretty picture of the streets. Their objective is to use this digital twin as a foundational platform, a base layer, to solve real urban problems, such as calculating the solar energy potential of every single rooftop or simulating traffic flows in the new Kalasatama district. They are transforming the model from a visual tool into an analytical engine. Before Helsinki could achieve this smart city vision, they had to overcome a massive problem that plagues almost every modern city: data fragmentation. In a typical city administration, different departments work in isolation. Architects design buildings using BIM, building information modeling, while urban planners look at the city map using GIS, geographic information systems. These two technologies rarely talk to each other efficiently. The energy department has its own data, and the traffic department has another. This creates data silos. When you want to analyze how a new building affects traffic and energy consumption simultaneously, you can't easily do it because the data formats are incompatible. The challenge for Helsinki was to break down these silos and create a unified platform where BIM, GIS, and real-time sensor data could exist together. They needed a common language to merge the static physical geometry with dynamic urban life. Helsinki's system architecture, illustrated in Figure 2 of the case study, relies on modular decomposition. Instead of treating the city as one massive 3D file, they use the CityGML standard to separate it into logical layers like buildings, transportation, and vegetation. This approach allows architects to analyze specific components, like green infrastructure, independently from the rest of the model. One of the most interesting aspects of the Helsinki case is that they actually generated two parallel digital twins, serving different purposes. On one side, we have the reality mesh model. This is created using high-resolution aerial photography. It looks incredibly realistic, like a video game or Google Earth. It is perfect for showing citizens what a new park will look like because it is visually stunning. However, it has a limitation: it's just a continuous surface. You cannot click on a single building to see its data, it's just a skin. On the other side, we have the semantic city information model, created with laser scanning, LiDAR. Visually, it looks simpler, almost like a cartoon. However, this model is intelligent. Every building is a separate object with a database attached to it. Planners use the semantic model for calculations, while they use the reality mesh for visual communication. The success of Helsinki lies in using both. Before we look at the Kalasatama case study, we must understand how the digital twin comes to life. This diagram, figure 5, represents the system's nervous system. It shows how a physical device, a thing, at a specific location, sends a continuous data stream to our model. This standardized flow is what allows us to plug in thousands of sensors, from traffic cameras to thermometers, without breaking the system. Moving from theory to practice, let's look at Kalasatama, which is the heart of Helsinki's smart city initiatives. This is a brownfield development project built on an old harbor area, designed to house 25,000 residents. Helsinki calls this district a living lab. The vision here is very specific: to give every resident 1 hour more a day. They aim to achieve this by optimizing logistics, traffic, and services so people waste less time waiting or commuting. The digital twin plays a crucial role here. Before a smart waste management system or a new traffic route is deployed, it is tested within the digital model of Kalasatama. The digital twin acts as the operating system for this district, integrating real-time data to ensure the ambitious goal of carbon neutrality by 2035 is met. It bridges the gap between the physical construction and the digital services. As we examine Helsinki's timeline, we see a clear evolution. They didn't start with a digital twin immediately. In 2008, the focus was purely on visualization. By 2016, they adopted semantic models where the computer understands objects. Now, they are in the digital twin phase, integrating real-time data to simulate urban scenarios, serving as a benchmark for modern smart cities. Remember in slide 7 when we talked about the semantic model and why it matters? This is exactly where it pays off. Because the digital twin understands the geometry, specifically the angle and area, of every roof in Helsinki, the system can run massive simulations. The city performed a comprehensive solar energy potential analysis. The algorithm calculated how much sunlight hits each roof surface throughout the year, accounting for shadows cast by neighboring buildings and trees. This isn't just data for scientists, it's a tool for property owners. A building manager can look at the digital twin and see exactly how much electricity they could generate if they installed solar panels. This application transforms the digital twin from a passive map into an active tool for sustainability and energy efficiency. A key application of this platform is energy analysis, as seen on figure. Helsinki uses the model to calculate the solar potential of every roof. Additionally, services like Katohukka visualize heat loss, helping building owners identify inefficient structures. This demonstrates how the digital twin translates complex data into actionable insights for sustainability. Finally, one of the most powerful applications of Helsinki's digital twin is social, not technical. In traditional planning, architects show complex 2D blueprints to the public, but most citizens find these hard to understand. This creates a communication gap. Helsinki uses its photorealistic reality mesh model to close this gap. When a new park or building is planned, it is placed into the digital twin. Citizens can virtually walk through the street, see the shadows, and understand the impact on their view. Tools like Maptionnaire allow residents to leave feedback directly on the 3D model. This democratizes urban planning. It ensures that the smart city is not just a top-down project imposed by engineers, but a collaborative effort built with the understanding and consent of the people living there. While Helsinki is a pioneer in open data, it is essential to look at other global leaders to understand the full potential of digital twins in planning. I want to highlight two distinct, best cases, Singapore and Rotterdam. First, Virtual Singapore. This is often considered the gold standard globally. It is a massive $73 million project covering the entire nation. Its most impressive feature is microclimate planning. Planners use the twin to simulate how a new skyscraper will affect wind flow and temperature in the neighborhood before it is built. It is a vital tool for sustainable urban design. Second, the Port of Rotterdam. This is an industrial application. They have installed sensors everywhere, even in the quay walls, to measure water levels and structural stress. Their ultimate goal is fascinating. They are building this digital twin to guide autonomous ships in the future. By 2030, the twin will act as the traffic controller for ships without captains. These examples show that whether for a city or a port, the digital twin is the future of infrastructure management. To summarize our presentation, we have seen a fundamental shift in how cities are planned. First, we learned that a digital twin is distinctly different from a traditional 3D model. While a model is static, a twin is dynamic, fed by real-time IoT data. Second, the Helsinki case study taught us that the biggest challenge is integration. By using open standards like City GML and adopting an open data policy, Helsinki successfully broke down the silos between different city departments. Finally, the benefits are clear. Whether it is calculating the solar potential of thousands of roofs in seconds or allowing citizens to virtually experience a new park in Kalasatama, the digital twin is no longer a luxury. It has become the essential operating system for building sustainable, smart cities. Here you can see the academic references used to prepare this case study analysis. Our primary source was the article, Urban Development with Dynamic Digital Twins in Helsinki City, published in IET Smart Cities. I have also included supplementary readings by Michael Batty and others for those who wish to dive deeper into the theoretical background of digital twins. This brings us to the end of my presentation. We have explored how Helsinki transformed from traditional modeling to a dynamic, data-driven smart city. I hope this case study has given you a clear perspective on the future of urban planning. Thank you very much for your attention.